And for the wonderful introduction. Hey everyone, as Deepa said, my name is Jigyasa Grover, and today we'll be talking about how we can sculpt the right kind of data for our machine learning models. The last couple of years have seen an immense growth of machine learning in multiple domains, from influencing our shopping lists to cars self-driving themselves around the town. Uh, Unquestionably, machine learning is the most used and the most abused subdomain of artificial intelligence presently. It is being wielded in improving healthcare, advancing warfare, from scrutinizing your resume to determining your creditworthiness. It can even create music and meaningful lyrics, and synthesize pictures and videos of non existent people, and so many other use cases. So, regardless of our fascination with the positive use cases or our loath for it, it is influencing our decision making power and dominating our lives heavily. Um, to describe machine learning, it would be enabling computers to learn on their own. And this is what encompasses the whole act of machine learning. The power of spotting patterns on their own, the requirement of like programming each and every detail is the biggest edge these decision making systems have over the others. Researchers keep traversing the unexplored territories of machine learning. And according to business experts, these businesses and organizations have just seen the tip of this algorithmic iceberg, if we may call so. According to Finances Online, there is has been 28.5 billion US dollars allocated to machine learning worldwide, and that was just like 3 years ago. So, and it is expected to grow to 40 billion US dollars by 2025, and it. And if you want to see the growth in the last 10 years, it started from a meager 1.3 US billion dollars, which has been like a huge investment. Almost 50% of the companies these days are either exploring or planning to do machine learning components in their future. And the number of startups focusing on just machine learning services have grown 14 times presently. 97% of the mobile users use machine learning trained voice assistants. And most of the search, you can say 40% of the search is powered just by voice. Enterprise domains like security, analytics, sales, marketing, they are reaching new heights with machine learning adoption of 25%, 33%, and 16%. The reason I wanted to talk about these numbers is so that you can gauge the impact machine learning has been having and the growth it is seeing across varied domains like search, security, analytics, sales, marketing, and all of these. Um, so, is machine learning the future? Of course. The dominant leaps are leaving the scientists, investors, policymakers, business leaders, and the audience bedazzled, with a hint that human like intelligence in machines is just around the corner. Nonetheless, you can say that the progress in machine learning has been impressive. But there's so much more to be explained, so much more to be examined, so much more to be researched upon, which keeps this growth and the investment going. To understand the state of the art machine learning algorithms, as we say, they are magic, but for them to work their magic, it's important to focus on three key dimensions: well calibrated data, sophisticated algorithms, and efficient computation. So sophisticated algorithms is something that comes with iteration. You can add, if you talk about deep neural networks, you can add as many layers, experiment with different architectures, and so on. Efficient computation, again, you can optimize, you can use more resources, with all these GPUs and TPUs present these days at one button click. It's definitely easier. But since we have progressed from the rule-based approaches to more data-driven approaches, it goes without saying that these machine learning algorithms are trained to capture implicit information from the data that we provide. It should have the power to kind of like detect these patterns and provide fascinating insights. So, in that sense, these modern day approaches are very, very data hungry. Without going into like many technical details, if you have like a brief understanding of how deep learning algorithms work, they have a lot many parameters, and the need to tune these parameters uh, requires that you have a lot of data in order to come up with somewhat generalizable model. So in that sense, having a lot of data is the key to coming up with good training sets for these approaches. So this kind of like emphasizes on the fact of quantity of data. Um, so worthy data collection, it forms the foundation of the pyramid of AI hierarchy of needs. So this hierarchy of needs is drawn parallel to what we have Maslow's hierarchy of human needs. This is drawn by Monica Rogati, who is a renowned data scientist and an AI advisor. Monica puts forward that data literacy, data collection, and data flow, all these form the basic needs which should be satisfied in order for us to achieve self-actualization, or nirvana, as they call in Maslow's hierarchy of human needs. In our case, it would particularly be the attainment of AI. So as you can see in this pyramid, you start with data collection, and this could be done via instrumentation, logging of data from sensors, external data, user-generated content on social media, and so on. And once you've collected, you have to create reliable data flows and infrastructure pipelines, ETL, for storage of this unstructured and structured data. After you've done this moving and storing, you need to explore and transform the data using process like cleaning, anomaly detection, preparation. And then you go on to doing aggregations, creating features out of them, analytics, creating training data sets. And further, more you can use this data that you have to optimize or to learn, you putting them into like simple ML algorithms, doing experimentation, and ultimately is when you would achieve AI. So it is very important to understand this pyramid, and as you grow up, the importance increases. uh, so once you understand the quantity aspect of it, it is also important to understand that the type of data that you feed into an algorithm has a profound effect on the success of the algorithm. It's mostly based on the principle of garbage in, garbage out. Peter Norvig has put in very simple terms called more data beats clever algorithms, but better data beats more data. So machine learning algorithms or models are as good as or as bad as the data that you have. As I said, garbage in, garbage out. Uh, so now we've understood the quantity and the quality aspect of data. We can move on to data curation aspect. So talking about academia, core machine learning and data science research groups in academia are mostly oriented towards novelty. They focus on advancing the field, many times weighing novelty more than the money making logic or performance scaling. So, in this attempt to work on newer problems, their only obstacles are not just finding collaborators from these pertinent domains, seeking funding for research projects. They also have to look for data sources in the absence of in-house data. Corporate giants, on the other hand, usually have access. These established organizations, they seldom have obstacles in obtaining computation power, hiring folks with expertise in corresponding domains, or accessing relevant data. The challenge, however, comes in scaling up the solutions to the massive user base they have. Any organizations like that would have tons of unstructured data at hand in the form of raw logs. But developing efficient data processing pipelines still remains a task. And for creating such resilient pipelines, apart from relevant technical knowledge, uh, the technical stack knowledge that you have, we also require the skills to identify and curate meaningful and unbiased data sets from the sea of unstructured data that we have. So these are the two different aspects of data curation, both from the points of industry as well as academia. And there can be different ways to approach building good quality data sets. And we can provide some structure regarding that soon. There are two different approaches that we'd be following. But before that, let's talk about three data sets that are also available on Kaggle that we've collected in the past. Which we'd be referring to as case studies, and you can also use them to kind of like further your research or just like play around with them. The first one is called clothing fit dataset. It contains fit feedback from customers on their purchased clothing items. and other information like ratings, reviews, category information, customer measurements, and so on. So this data set was collected specifically to tackle product size recommendation problem. Given a user, given a product, you have to find the best size that would fit them. So we had this problem in mind, and keeping that problem in mind, we kind of like created this data set. The next data set that I'm referring to is called the sarcasm detection data set. So past studies for sarcasm detection tasks have mostly used data from Twitter, but they end up being noisy in terms of like label assignments and the type of language used. So to overcome these limitations, we have used two different websites, The Onion, which contains sarcastic articles on current events, and HuffPost, which contains reports of the real news. So using this data set of sarcastic and non-sarcastic news, you can train a model which can, automatically help you identify those. Again, we'll come back to this, but let me introduce you to the third data set we have for our case study or examples, would be the news category data set. Now, this was created without any specific problem in mind, and it is extracted from HuffPost. It contains about 200,000 news headlines along with the category they belong to. These data sets have been doing pretty well on Kaggle. And if you're like new to machine learning or you just want to get your hands dirty and try out simple data sets, definitely check these out. They not only they are good for small term projects, but they have also furthered research globally. So now circling back to the approaches on building good quality data sets, like my co-author built these three data sets, and what was the approach, what was the mindset behind it, and what was the reason of the success. So considering the situation where we usually have a specific problem in mind, let's say I have a problem in mind that I feel like I can very well solve with machine learning. In that case, we usually can say we have a North Star that we want to follow. And that case, we have like a guided search approach. For example, the clothing fit data set and the sarcasm data set, they kind of like fall under the guided search approach category because we had a problem in mind that we were seeking to solve using machine learning and data. On the other hand, the last data set that we talked about, the category data set, that was created without any particular problem in mind. That was created because we were just curious and we wanted some interesting data points. And that was enough to kind of like fuel that wanderlust, if I may say so. So both these situations have their own challenges, and today we can learn how to kind of like overcome them and what should be your thought process behind building any of such data set. So the first approach is the guided search approach. As I mentioned, when we have a specific problem in mind that I'm seeking to solve using machine learning and data, we have to build a data set to address that. We go with the guided search approach. The biggest challenge of this guided search approach is the understanding of problem in and out. It can definitely be a daunting task, but let's share some pointers and examples on how we were able to do that and how you can do the same. So as I said, the first step to this approach is defining your problem in a very simple manner. So to give you an example for the size recommendation problem that we had in mind, corresponding to which we build the clothing fit dataset, our problem was given a user and given a product with different sizes, recommend a product size that fits the user the best. So let's say I'm in the market to buy a pair of jeans. They are available in size, let's say 2 to 22, whatever. The task is to recommend me the best size that fit me. And it would be based on my past purchases of users that are similar to me, and so on. So that is your formal problem statement. And one thing to note in this formal problem statement is the essential data. The essential data we have kind of like highlighted would be the essential signals that are very important in kind of like solving this problem. For example, without a user, this problem is unsolvable or like does not even exist. Same goes for a product. So in this case, the user ID, the product ID, the size I purchased, and the feedback, like was it too tight, was it too large, was it fitting perfectly, that is a fit feedback. So these four kind of form the essential data signal that we have. And no doubt in the fact that we can collect other data signals for a transaction, like, what was the category of the product, what was my age, what were my measurements, and so on. But they might not be of absolute necessity. Um, so this is the second step that you should always be doing, like identifying the most essential data signal that you have. And another consideration while collecting a data source is if the source contains enough historical data to construct the sufficiently large data set that we want to build. Going back to the previous note that we shared, that since modern day approaches are data hungry, it's very important to have like a big chunk of data for it to have like more generalizable pattern. So, instances where it would not work out would be the retailer that you're trying to, like source your data from does not have enough customer reviews reporting the feedback. There are many times you'd buy a product and you might not report, whether it fit you or not. So that is the case. Or let's say the news source that you're trying to fetch the data from does not have an archive of old posts. It only has like posts up to last 7 days. So that might not work because the corresponding machine learning model might not be able to learn suitable model parameters to capture patterns in such an underpowered data set. In cases like these, it would be very wise to combine data from multiple smaller sources, or maybe venture out to find a singular source to provide a large enough data set. So after you've determined the volume, as I said, it should contain enough historical data to construct a sufficiently large data set. Last point comes up is a uniqueness, which we can also cover in the unguided search approach. So coming to unguided search, for creative people who are planning to fashion a unique and a worthwhile data set, and they do not have like a specific problem in mind which they are planning to address, unguided search is the way to go. Let's think about the news category data set. As I said, it was built without any specific problem in mind, and it's an excellent example of this approach. The biggest challenge for unguided search of data sets is that it involves a lot of uncertainty. Since we are not sure what our problem is, we are not sure what data signals that are of absolute necessity in our data set. So there's no proper structure for the consequence search operation that we need to carry out. Although you can think of it the other way around, that not knowing the problem makes things easier or difficult in this case, but let's try to bring some structure to our search. So one of the biggest signs of a competent data set is that its signals can be utilized to address some practical problems. Or it could also have the ability to help us lead to fascinating insights into some, trending phenomenon, or like recent trends that you're having. So for example, training a classifier on the news category data set, you can help solve various problems. You can help identify a prose's writing style, whether it's political, has a humorous tone, is a criminal report based on latest fashion trends, or so on. Furthermore, it can also be help to tag untracked news articles or to understand the writing styles and how they differ for different news categories. So that is something that you have to keep in mind, that even though you don't have a problem, your data should be unique enough or might lead to like fascinating insights. So as I said, you can have different possibilities with the same data set. Once you've identified that a data signal might be worth estimating in your data set, it is also necessary to ensure that the web source that you have provides enough side information for the given prediction task or for the potential prediction task. Side information could also be called metadata. And if it's not present, then we should at least have the ability or scope to join to some other data sources to make that possible. For example, predicting a product's price from just the essential data signals might not go very well if you do not have enough metadata associated to it. For example, the brand of the product, the fabric of the product, is it stretchable or not? So all of these side information or metadata definitely help to kind of like augment the prediction task and make it much more generalizable. Third, we have the data volume requirement. Of course, it applies here as well as compared to guided search, but of course, it has a more relaxed constraint since we do not have a specific problem in mind that kind of like binds us. Based on the data availability that we have, we can modify the potential problem statements. However, we have to make sure that the resulting problem is still an interesting one to solve. To give you an example, in the news category dataset, the first pass that we did, we had many categories with less than, say, 100 headlines. Since we don't have a problem definition necessitating the prediction of infrequent classes or like anomaly detection, we can remove those corresponding records from the dataset. They might be acting more of as an outlier. This way, the learning algorithm is more balanced. The data set is more balanced, and the learning algorithm can determine better parameters for the remaining classes that it has. So definitely a data volume requirement applies here as well, but it has a more relaxed requirement set as compared to the guided search approach. Lastly, before trying to extract any data set, be it in guided search or unguided search, always make sure that you kind of check the online resources, online repositories, if any of the such data set already exist. If there is, we should definitely evaluate on what we are trying to build, what it contributes on top of the existing one. This is to ensure that we're contributing something novel to the community and also saving on our efforts, time, energy, and so on. So once you think that you have built a data set, extracting the data set is, maybe in like a CSV or whatever format that you have, might not be enough. You have to work on top of it, on the extracted data that you have, to eliminate impurities that might have crept in before feeding into a machine learning model. So you can think of the next steps as grooming of your data set. And we can talk about a few steps that you should be performing before moving on to the feature engineering or like making it ingestible enough for a machine learning model. So our data that we have, it would not help a machine learning model, no matter how sophisticated your model is, if the essential data signals are missing. So for example, if you have, let's talk about the clothing fit recommendation, clothing fit data set for the size recommendation problem that we had. Let's say the reviews are missing. So you do not have essential data signals like the fit feedback or the size purchased. We need to either remove those transactions from our data or find a way to impute those or provide the essential data signals with the existing information that we have. So this process of excluding specific values due to their irrelevance, due to their redundancy, or due to any extremity, like the size is what, say, x to the power 10L, that doesn't really make sense. So that is kind of like an extremity, or you would have to like trim it out. So that is something that should be kept in mind. Your data should be clean enough, and it won't help a machine learning model if most of their data signals are missing. So you could definitely trim them out or impute them or find ways to kind of like fill in those gaps. Coming to the next segment that we have, it is in an ideal scenario, you would think that building a data set using one and only source. For example, for the clothing fit data set, we used ModCloth as our source. However, there would be many circumstances where you would not have the entire data that you want from one single source. As we talked about, we need to have a balanced data set, and data volume requirement is also something that kind of like binds us. So you would have to like go to different sources to gather bits of attributes from different ones and have a more meaningful, inclusive, and valuable data set. So coalescing the data from separate sources to provide a unified view is what is called data integration. We can do data integration in two ways. The first one is vertical integration. So recall the sarcasm detection problem that we had, where we collected data from two websites, The Onion and The HuffPost. So The Onion provided sarcastic versions of current affairs, whereas HuffPost reported the real and the non-sarcastic news. To create the final data set, we had to fuse the records collected from the respective sources by appending them vertically, since they shared the same attributes, let's say article link, headline, and a sarcastic label. So it was easier to connect them to form a data set having both sarcastic and non-sarcastic records in a comparable number. So that way you were kind of like integrating vertically, across the same attributes. Uh, the second case could be when you're doing horizontal integration. Consider a task where you have to build a data set regarding different cities globally, containing different fields like state, country, area, population, climate, pollution, civic administration, religion, languages, festivals, cuisine, whatever. Um, and it is very likely that you would need to refer to multiple sources from the web to gather all of this information. It is not possible that you'd find them at one place in the most desired format. So some attributes like state, country, area, population, they might be available from one source, whereas information about demographics and culture might be available from other. So in this case, you'd be joining them based on the city ID that you have, let's say. So that way it is more of like horizontal data integration because you are integrating different attributes for the same record. So definitely when you're building a data set, you have to make sure that the data set that you have, it should be balanced. It should have all the essential data signals. And in case the source that you're referring to does not have all of these, you can try doing data integration from different parts, different sources, as I said, vertical, horizontal, and there would be many cases where you would have to do both. So that would be a more complex task, but surely not impossible. So once you've integrated the data, you've trimmed out the unnecessary part. Now comes the transformation part. Um, Consider there's so much content these days available on the web that it is impossible for a human to check the correctness of all, um, and even moderate it. The content posted by a publisher, let's say the clothing fit data set, the content posted by a publisher, like the name of the product, the sizing chart, the description, these all are something that can be moderated easily, but you cannot moderate a user's content, like the review they post or based on the product quality or the size, the body measurements, which we might try to blatantly feed to the machine learning model. It could definitely turn out to be noisy. So it is very necessary to scrub the data set that we have using specific techniques, build a quality data set, for example, bringing the date into same formats, or like handling special characters, handling grammar, spelling error, using NLP techniques like lemmatization, stemming, etc. Encoding the sizes that you have in numerical order and so on. So basically, data transformation's primary focus is to scrub the data set's raw values, remove redundancies, correct the language, logical semantics, and so on. So this is again something that you should be focusing on. And as I said, some cues include handling special characters, encoding, and so on. So once you've transformed the data, the next step usually is feature engineering. Feature engineering is one of the key techniques that often does not get its due limelight. Much of the success of machine learning is actually success in engineering features that a learner can understand. It has many a times been referred to as applied machine learning. So feature engineering is nothing but applied machine learning. And this is where your intuition comes into play, your creativity and black art, as you say, mostly intuition. Um, this step is much more important than the actual model, as an ML algorithm only learns from the data that we provided. And choosing the right features in the right format can by far boost the performance of using even simpler ML models. Like consider a case where you have a data set and you have two models, one very sophisticated one, a simple one. You'd assume that the sophisticated one's going to perform well. But if you do feature engineering on the data set that you have and then provide it to a simple ML model, there are chances that the simple one outperforms the sophisticated one. So definitely it helps in boosting the performance, but also it increases the transparency of the model. It is much easier to understand how the model is making predictions. And furthermore, as I said, since it boosts the performance of even the simple ML models, it reduces the need to use heavy ensemble learning techniques. So ensemble learning are nothing but a combination of different ML models. For example, consider using neural network and logistic regression all into one, and so on, kind of these things, or just combining different architectures, to give you an example. Furthermore, it reduces the need for tuning the hyperparameters and their optimization. You need not like tune it to the very T. A bit of hyperparameter tuning definitely works. So that being, the bottom line that I want to focus on here would be that there are many other processes apart from the modeling part that you usually focus on, before which the data becomes ready to be fed into the ML model. Consider a machine learning workflow to look like this. You start, this could be in any organization or any research group or any problem that you're solving. You usually think of the problem statement, define it in a very formal way. And after that, you develop an intuition of how ML can help you tackle that problem, its challenges, documenting the ins and the outs. Once you've done that, the focus is mostly on like how do we get the data, on sourcing the data, fabricating your own data set, and then processing the data set, doing all the data set pre-processing stuff that we talked about, doing feature engineering and so on. And once you think that your data set is ready, you define the metrics that would. This could also come during formal problem definition, is you define appropriate metrics to define the success or measure the success of the intelligent solution that you're planning to build. And once you've defined that, next you move on to choosing the appropriate model, the most complex architecture or the learning algorithm to address the problem at hand. And once you have the data and the model ready, you feed the data into the model, deploy the model, monitor the predictions that you have, and then make ways of maintaining the new streams of data that might be coming in, refreshing model parameters here and there, and that's it. That's the basic workflow of a machine learning model that you have, or machine learning pipeline or task. Most of the days, and so far, the focus has been on defining appropriate metrics of success for the intelligent solution. Like what metric would be of absolute necessity and would make our would showcase the positive gains or the positive impact that we have. And the next big thing is, of course, choosing the appropriate model and the learning algorithm. You definitely, people focus on, let's add one more layer, let's have this complex architecture and so on. So far, the focus has always been on this part of the machine learning workflow. But research and studies have revealed that it's high time that we start focusing on the above aspect of workflow. That is, how are we sourcing the data? How are we processing the data? How are we engineering features for it and keeping the model static? And this is something that should be the focus of today. Andrew Ng, who is the AI expert, also tweeted a while back that AI systems is nothing but code and data. Code is like model or algorithm. And most of the academic benchmarks, competitions, they usually have the data fixed. They'll give you, let's say a file with data and say, here is the data, create a model that would perform the best on it. So, so the organizations have mostly kept the data static and worked on code, but it's high time now that we keep the code static and massage the data and work on the data, do a lot more data processing, feature engineering. All of this give more importance to this aspect of machine learning workflow. And this is what comprises the whole aspect of data-centric AI. You have to focus on data. You have to focus on where the data is coming from, what is the quality of data, what is the quantity of data, how are you processing it, the different techniques that you could use. And this is what is also the premise of my book. I've co-authored it with Rishabh. The book's called Sculpting Data for ML, and it is the first act of machine learning. You can definitely check out the book on Amazon. It talks about, the book is divided into 5 different chapters. The 5th chapter kind of like gives you an overview of machine learning from a data perspective. But most of it, the book's focus is on significance of data in machine learning, and it helps you identify relevant data signals. And it is a very hands-on book, so you'll find code examples in Python using Beautiful Soup, Selenium, Chrome. And it's a step-by-step guide on how you can create your own data sets. So the three data sets that I was talking to you previously, the clothing fit, sarcasm, and news category, these were built using the code provided in this book. You can definitely use this to build your own data set. And apart from it, it also has a synopsis of all the data pre-processing techniques. It talks about, bucketization, symmetric or quantile, different feature engineering tricks you can use, how to leverage automatic feature engineering, doing feature importance analysis, so that you don't have like a ton of features in your model, avoiding feature explosion and so on. And ultimately, as I said, the last part of your entire pipeline should be application of machine learning model, but from a more data centric point of view. So definitely check this out. It has been endorsed by leading ML experts, Julian Macaulay, Lawrence Murney, Meng Timon. I'm pretty sure you're aware of Lawrence. He's very popular in the AI ML circle. And with that, I would like to actually leave last few minutes to take questions, because I think these kind of talks are really helpful. But what is more helpful if you can get like a few of your questions answered? So happy to answer any of your questions. Leave them in the chat box. And thank you so much for having me today.
If you have any questions for Jigyasa, please post it to her. She would be able to. You can post it on the chat box. We'll have to get the book. Okay.
Sure. I can try sharing the link as well if you want.
Yeah. Can you share that link again here, Jigyasa? I know
Yeah,
you
sure.
shared the QR code here.